Hey guys, well, welcome to chapter 13. Moving right along with our material. We'll be losing Jeff, but we'll be gaining, I don't know what we'll be gaining, but I'm sure it's something. So chapter 13 is the second and third of essentially a three-part conversation about how to calculate stuff that's in motion. And let me switch screens here, excuse me, switch cameras. I'll show you what I mean. So in chapter 12, we talked about Newton's second law, F equals ma, and we calculated the mostly the acceleration or the force that was causing it, sometimes the mass. And the central idea was to use Newton's second law in a whole bunch of different ways. Well, chapter 13, in chapter 13, we're still analyzing the same things. We're interested in motion, acceleration, forces, but we're going to do it in a little bit different frame. And we're going to start with work, energy, and power. And then we're going to end with impulse and impact. So essentially, chapter 13 is two chapters with two sections each, right? So we'll have four sections of chapter 13. So to kick us off, I wanted to have a little bit of a conversation about the math behind this. I don't want to bog you down too much, so we'll talk about it. I'll introduce some of these concepts. You should probably take notes, and then we'll move on. So as noted, we are talking about work, energy, and power, and we can probably add eta, and we'll get into that a little bit later on. Efficiency. So what is work? What is energy? Work is the ability to supply force and to change, and a change in distance to an object. So force, distance, right? We're familiar with that. Force times distance, right? So we'll say dx for the time being. What is energy? Energy is the ability to do work, right? Okay, well, that is simple enough. And question is, where does this come from? Well, it actually comes from Newton's second law. So we draw a line here, keep us organized. And so if we start with F equals ma, we have done this expansion before, and this is m, and a is what, dv dt? dv dt, and we can expand this to m dv dx dt. And remember, this is v, right? So then this becomes mv dx, not dx, dv dx. So bringing this down a row, what do we have? We have f, and I'm going to move this differential. So I'm going to say f dx equals mv dv. And for the time being, let's just talk about this later, right? So this is really what I wanted to focus on. And what we call this, in, I think it comes from thermodynamics. I tried to look it up, but I couldn't find an answer for it. But du, so work, this is U is the symbol we use for work, is equal to F dx. Okay, so the derivative of work is equal to F times the derivative of motion. When we integrate this, then we get U from 1 to 2 is equal to, let's go and put this here, and we usually use A1 to A2. It doesn't matter in this context because what we're really talking about is force times some change in distance, dx, in general. So in this first section, we're gonna look first at work, and then we're gonna look at energy. So, and energy is where we start to deal with this guy here. But it turns out that there are essentially three kinds of work that we're going to look at specifically. Oh, by the way, work and energy, not the same thing. Anybody says that? They're real close, and I'll show you why you can use them interchangeably when we get there. But in general, we have three kinds of work. So we'll keep this, and more specifically, we'll keep this relationship right here. And I want to note here that these guys have the same units. Okay, and we'll just copy this equation. So du equals F dx. All right. All right, so three kinds of work that we're going to look at. One, constant force. And this is really the classic definition. We had it when we derived this, and it is U 1 to 2. So this is the work done from 1 to 2 equals F times some change in position. So I'm calling it X here. It could be S, it could be Y, it could be R. It makes no difference. 2, work done by a spring. Actually, let's do weight. Doesn't matter. Okay, so here, U1 to 2 is equal to minus W delta Y. We could expand on that if we wanted to and talk about space, work done in space, but we're not going to have any problems that deal specifically with that. And so we'll come back to space mechanics a little bit later in the chapter, but for now, we'll just bypass it. Something to keep in mind here, and Jeff goes over this, is if you have a particle moving along this trajectory, and we'll draw it as a little box here, fill it in so that it's confusing. This Y is from here to say here, and let's just say that our box goes from here, goes to there, right? So it's going up. And if our coordinates, we're calling this Y and calling this X, then the work done by the weight, in this case, is only the change in Y. It does not include the change in X. So it is directionally specific. Third, and notice this is not potential energy. This is the work done by the weight. There's a meaningful difference that we will come back to. Third, work done by a spring. Okay, and a spring, so we got here U, 1 to 2, equals, it's an integral, again, from A1 to A2, or P1 to P2, usually minus kx dx, right? So the force of the spring is dependent on its position. You compress a spring and it gets harder and harder to push. So when we integrate this, here's where we get some familiar looking equations. We get 1/2 kx squared. See, this is minus, so this would be 1 minus 1/2 kx 2 squared, right? And this taken together is the work, right? Because recall that we need a change in x. So the change from here to here is the work done by the spring. Okay, so we'll, in some of Jeff's videos, he will be using these early on in a single example. And I just wanted you guys to have a peek at the math of these before you get in and you're looking at it. It should be mostly reviewed. What comes next? Let's see. So back to, yes, hopefully you got it. If not, pause. Okay, so back to this equation that I was deriving, or that I derived. What did we have? We had u, 1 to 2, wait, this was our f, equals, and that was mv and then dv, right? So again, this is the same as the, let's call it from position 1 to position 2, and this is, this should look very familiar. So this is 1/2 mv2 squared minus 1/2 mv1 squared. This is kinetic energy, right? And the meaningful distinction here is that this is kinetic energy at one place. This is kinetic energy at a different place. They are both kinetic energy. So this gives rise to this idea, for some reason, and I have no idea why, in thermo, they introduce a variable t, which is 1/2 mv squared. This is the generic, no subscripts version. So if we wanted to rewrite this in terms of t and u, then we would say that u 1 to 2 equals T2 minus T1. And this is usually rewritten as T1 plus U1 to 2 equals T2. Okay, so I don't want to go too much further with this. Just check my notes, make sure that if there's anything else that I wanted to cover. Oh, right, efficiency, power and efficiency. So power is, again, looking at two different ways of looking at the same thing. Power, so let's add that. Power, which is conceptually, it's a very small step from work and energy to power. Power is F times V. It's a rate. And if you expand the V, then that is F times dx. over dt, right? And this being a differential, so essentially it is work turned into a rate. So it's the rate of work, which makes sense, right? Because we know that joules are, or excuse, yeah, watts are joules per second. So, right, okay. So there's not a lot to know beyond that. Power is literally just the time derivative of work and energy. Lastly, eta, efficiency, this is, well, you're in luck. This is the simplest thing that you're going to learn probably throughout mechanics. So this is power output over power input. That's it. That's all it is. It actually never really gets more complicated than that. We will look at some examples, and in the next block, I think we start talking about we talk about the conservation of energy, and we talk about what potential energy is. The way that I keep it straight, this section from the next, is that the 1 to 2 here, to me, indicates a straight line. And when we start making the distinction about potential energy, we start talking, we're no longer talking about work, we're talking about potential energy, which is, that's essentially energy that cycles based on position. And we'll get into that. But at any rate, I hope you enjoyed the videos. This is our last set with Jeff. And like I said, I just wanted to jump in and offer a little bit of the mathematical background before we head on into it. So have fun, and I will see you in class.